press record. Thank you for reminding me. You guys are great. Yes, so, all right, Michael, yeah, thanks. So we see that e to the x is between 0 and 1 whenever, according to the graph, right? Whenever x is negative, whenever we're on the negative part of the x-axis. So we can say that e to the x is between 0 and 1 whenever, or for x's which are strictly less than 0. Thank you for the links. Okay, so that of course leaves the remaining to complete the thought there, right? You see that e to the x is greater than 1 for x's which are positive, strictly greater than 0. All right. So keeping that in mind, these kind of notes just by knowing the graph, you can maybe do an example. Maybe I'll leave. If we have a function, and I'm already going to factor it, e to the x times e to the x minus 1 times e to the x plus 2. So this is the kind of thing you'll have to be able to do in calculus after you actually do the calculus, and you're just doing cleanup work. This is the kind of algebra that's required here. When is this function, in our example, equal to 0? When is it positive? And where is it negative? Right, so anytime you, of course the domain is all x's, all real numbers. These are just purely exponentials and being multiplied and so forth. But so we learned that, of course, if you want to know where the function is positive and negative, you know, to find everywhere, it's best first to find where the function is equal to 0, which will cut up or partition your number line, and then you can choose test points for the remaining intervals. So that's the x-axis. Okay, so if we set the function equal to 0, we know that we factor because it's easy to see when a product of numbers is 0. So either e to the x is 0, or e to the x minus 1 is 0, or e to the x plus 2 is 0, right? Okay. However, if you look at case number 1, I'll highlight that in yellow. Is that possible? Yeah. Of course, right? Because as we noted before, e to the x is always strictly positive, so strictly greater than 0. Not possible. So that's not, doesn't yield a solution there. What about the second factor? Is it possible that that's equal to 0? Yes. Right. We know that's the same thing as saying e to the x is 1, and with our knowledge of exponentials, we know that when x is 0, e to the 0 is 1. So when x is 0, so that's going to be a place where our function is 0. Okay. And what about the last factor? If I could erase this highlight. Okay. Is it possible that e to the x plus 2 is equal to 0?
It is possible.
Actually, the sound is really low for me, so could you repeat that? No, no is correct, question mark, right? With confidence. All right, it's not possible, because that's saying that e to the x would have to be negative 2, and we already note that that's not possible, so not possible. So there's only one value of x where this particular function is 0. Right. So now we can choose the remaining, or look at the intervals that we, right? So when x equals 0 cuts up our number line into two big intervals. And from each interval, we're going to choose a test point. Let's say, well, it doesn't matter, x equals 1, x equals negative. We can also do something more thoughtful and just pretend that we're choosing an x that's extremely large, right? So any x value to the right of 0, you can just do a little mental experiment. Just say, choose an x that's large and just imagine what happens. Okay. In which case, first factor, well, it's e to the x. It's always positive. So maybe we should write that down. I'm not going to waste too much time on this problem, but the first x is 1, we get just e, right? That's positive. All right, and then e to the x minus 1. Well, we learned that e to the x, if we look at this, e to the x is greater than 1 whenever x is greater than 0, right? So since e to the x is greater than 1, that means if you subtract 1 from each side of the inequality, you see that e to the x minus 1 is positive. Of course, on your own, you can use a calculator to plug that in. And this will always be positive as well, right? Because it's just e to the x plus 2, e to the x is already positive, plus 2 is even more positive. So now for the other interval from negative infinity to 0, right? You're going to quickly train yourself to see that e to the x is positive regardless of x. E to the x plus 2 is even more positive. It's just that the middle factor here would be negative. Oops. So positive times negative times positive is negative. And that stems from the fact that since x is less than 0, we know that e to the x is between 0 and 1. Subtracting 1 from both sides, you see that our factor in the middle is less than 0, so negative. Let me try to follow the. Okay, so we have two good questions. Somebody wanted to know, how do we know that e to the x minus 1 is positive or negative? Okay. So let's look at, so we know that x is 0, e to the 0 is just positive 1, right? If we take a value of x which is greater than 0, we know that e to the x is greater than 1. And that's, well, you know, e to the 1, e is the number that's greater than 2. So it's greater than 2 is greater than 1, also from the graph. The graph is above the line where y equals 1. So greater than 1. And so without a calculator, that way I'm thinking about this is I'm subtracting 1 from both sides of this inequality. And that way I see that my factor, e to the x minus 1, would be greater than 0, i.e. positive. Now, if we choose a value of x to the left of 0, so smaller than 0, from the graph, we see that e to the x is smaller than 1. And subtracting 1 from both sides, we get that e to the x minus 1 on the left is less than 0 on the right, i.e. it's negative. So e to the x minus 1 here is positive. Here it's negative. So that's kind of analysis that's required. Okay, that's kind of pre-calculus prerequisite. And also had a question that says, why is e to the x plus 2 positive if it's not possible? We didn't say that it's not possible. We said that e to the x plus 2 cannot equal 0, right? because e to the x is already greater than 0. So if you add 2 to both sides, you see that e to the x plus 2 is greater than 2. So it can't be, it has to be positive. It's just that it can't equal 0. Okay. And then I guess we would want to complete the answer by using an notation. So this function is positive on the positive part of the number line, and it's negative on the negative part of the number line. Okay. Okay, not too bad. I am going to move on if there are no more questions regarding that example or anything previous. Okay. I do want to copy. Oh, right. All right, so we're going to draw y equals e to the x, your basic exponential function again. So another skill in calculus would be to kind of find the limiting behavior, the kind of long-term behavior of your function. So we want to look at what happens if x gets very positive, very large. So what happens if x gets very large? So that's very kind of loosely speaking, not very precise math terminology, very positive. Maybe a better way to say this is maybe we can try to complete this phrase as x goes to, or maybe tends to, or approaches, even though that's kind of weird, goes or tends to. So this is really getting the theme of calculus now. We're thinking asymptotically long-term behaviors. As x goes to positive infinity, how does e to the x behave? Where does it go? Yes, y gets very positive. It goes to infinity. Yeah, I mean, as we say, like in the trade, right? The function blows up as x gets very positive. The corresponding y values also get very positive. I mean, it's exponential growth. What do you expect, right? It better blow up. Awesome. Okay, and of course that raises a natural question. We're just looking at, what we're doing is just looking at the exponential function. I want to emphasize that you need to be familiar with it, domain, range, where it's positive, negative, so you can do sign analysis, also the long-term behavior, asymptotic behavior of the function. Okay. So this raises the next question. I hope you anticipated it. What happens x gets very negative to our exponential function? So maybe we can complete the phrase as x goes to or tends to negative infinity, e to the x does what? How does it behave? What do the y values do? It approaches 0. Very good. So from the graph, you see that if the x values, and I'm drawing these x values on the x-axis, are getting more and more negative, so x goes to negative infinity, the corresponding y values are approaching 0. I mean, the graph gets closer to 0. So e to the x goes to 0, or approaches 0 in this case. It's a finite number. So maybe, because it doesn't get to 0, right? It just approaches. Okay. So does the exponential function have a horizontal asymptote?
Yes.
Yes. And the horizontal asymptote is the horizontal line. And so what's the equation of that horizontal line?
X equals 0.
So maybe this is a good side note. If I have a horizontal line, now every line in the plane has an equation. What's the equation of this horizontal line? So suppose it goes through has a y-intercept of 3 or something. What's the equation of this line? Yeah, y equals 3, right? We're not saying that y equals 3. We're not just referring to this point. I mean, the graph of that equation is all points in the plane where y equals 3. And that says nothing about x, right? It has no restrictions on x. X could be anything. So the collection of all such points which satisfy this condition is a horizontal line. Okay? So your horizontal asymptotes are going to be in the form, because they're horizontal lines, will be in the form of y equals a constant. For the exponential function, we see that the graph approaches the x-axis, which is just a horizontal line where y equals 0, right? All points on the x-axis have a y coordinate. These are awesome. All right. Okay, that's great. So we did mention what happens to the exponential function as x becomes very positive, the function blows up, and what happens to the exponential function as x goes to negative infinity, it approaches. So for computing limits, you're going to have to know that exponential. Right. Okay. So now we're going to remind ourselves of some exponential properties. I mean, the properties of exponents, they hold for the exponential function, right? So let's look at the properties of a reminder for the properties of the exponential function. All right. So e to the, let's say a plus b is the same as e to the a times e to the b, right? So in a sense, exponentiation turns addition into a multiplication of exponentials. Maybe you need to know that if you have a negative exponent, that's the same thing as finding the reciprocal, right? So 1 over e to the a. And we have e to the a, and the whole thing raised to the power b. Just as a reminder, is that's where you multiply. Okay. So I guess that's not really surprising if you really want to think about it. If exponentiation turns addition into products of exponentials, well, okay, I won't go into it. Okay. All right. So what's going to be relevant here is where they're going to be disguising. You're going to have polynomials, but instead of x, you're going to get like e to the x, right? So we need to know how to reconceptualize or re-express these kind of things. Say e to the 100x or something like that. And make sure we are able to distinguish that from, let's say, e to the x plus 2 or something like that, e to the x plus 3. So for the first column in this example, we would be using essentially property number 3. So e to the 2x, we're going to sometimes need to rethink as e to the x whole quantity squared, right? By property 3, you would multiply the exponents here. I think Elliot showed me that, or mentioned that you can't see what I'm pointing to. Yeah, it doesn't look like, oh, you see. Okay. So e to the x quantity squared is the same thing as e to the 2x. e to the power 3 times x is e to the x cubed. So, of course, the reason we need to be able to do this is we need to find those disguised polynomials where instead of x we had e to the x, and so on and so forth. In the second column, you're using property number 1, right? So this is e to the x times e squared. So a constant times exponential function. E to the x plus 3, we can write that as e to the power 3, so that's just a constant times e to the x, and so on. Awesome. Okay. So the next example using this idea to demonstrate what I'm referring to about seeing a polynomial in e to the x as opposed to just x. So here's a function. And we want to go through the same exercise of figuring out where this function is 0, if at all, where it's positive and where it's negative. So does anybody have any idea how to start this? Or does anybody, can anybody restate what we're looking at, I guess? It's going to involve the word polynomial, not in x, but in e to the x, right? That's the kind of thing to see. Sure, factor out, right? So using the previous example, we can think of e to the 3x as e to the x cubed. E to the 2x is e to the x quantity squared. That's just e to the x. Right? So if you temporarily just declare, just maybe for clarity's sake, if u is e to the x, what are you really looking at? Well, you're looking at a cubic. If you replace e to the x with u, there's no confusion there. That's a polynomial, degree 3. So you'd factor out a u. And then after factoring out that u, you have a remaining factor was a quadratic, which I guess we can factor, I believe. So, yeah. And we know we can now back substitute. We know that u will be e to the x. And really, this is the same problem I did above, by the way. Right. So now you can refer, if you want to know where this is 0, when x is 0, when it's negative, or positive first. That's for x is greater than 0, and negative would be when x is less than 0. Because it's exactly the same example, I haven't bothered numbering these, unfortunately. But it's the same example that we had over here. But anyway, I just wanted to illustrate that you need to recognize a polynomial when it's not just x, but maybe some other function. Awesome. I think, I don't know, do you have any more questions about exponentials? Because it is maybe 5 minutes over what I expected to. You didn't understand the last part I did. Let's see. Okay. All right, so we recognize that this function is really a polynomial in e to the x. So we were able to factor like any other polynomial, but we have e to the x, right? And now we would find where this function is 0, positive, negative. We would have factored already. And you first find where it's equal to 0. And then we know that the product of 3 factors is 0 as soon as one of the factors is 0. So either e to the x is 0, which is not possible. Exponential is greater than 0. So no solution there. or when e to the x plus 2 is 0, which again is not possible, because e to the x is positive, plus 2 is even more positive. And the only place we found that the function is 0 is when the last factor is 0. That is possible because that's equivalent to saying e to the x equals 1, after you add 1 to both sides. And we know that happens when x is 0. So the place where the function is 0 on the x-axis is when x is 0. So maybe that's a little confusing. The function is 0 when x is 0, but okay. And then we would have chosen test points. Okay. Oh, yeah, so somebody asked a question. Yeah, I mean, I'm just doing this for illustration's sake, where you do that substitution, replace e to the x with u. I mean, I would just have gone straight from here to here, right? But I just wanted to make sure it's clear that if you replace e to the x with some letter, then you'd be looking at a polynomial in u, and when you back substitute, you really have a polynomial in e to the x. Yeah, but I would have definitely, if I was doing this on my own and it's test time and I want to save time, yeah, I wouldn't formally, I don't think you need to show that formally. Well, the direct way would be to, without the u sub, is just start with this and notice that you can factor out e to the x, and then you would have, yeah, all right, you factor out e to the x, which would leave you with e to the x squared plus e to the x minus 2. And then you would have to see that you can factor this, right? But I don't want to do the shortcut. Sometimes you have to take the scenic route, to appreciate the shortcut that will come through with experience. Cool. All right, so can anybody guess what we're going to be talking about next? What function? We just talked about the exponential function. Yeah, we're going to talk about the log function. The e to the, well, whatever, I won't say. All right. Okay, so here's a basic graph of y equals log. Log here, I mean, there are many bases for your log functions, but the one that we care about, at least in calculus at the moment, is base e, the natural log, right? A log natural, whatever the French word is. It's natural log, but backwards because it's French grammar. So that's just a log function based the number e. All right, so again, just if you know this graph, what can you say about the domain of log?
May I say?
Yeah, the domain is all positive numbers, right? The graph only exists for x's which are positive, strictly greater than 0. So the domain is where x's are. In other words, you can't say log of a negative number, right? It's just using real numbers, it just doesn't work. You can't say log of 0 either. That's also not defined. The only thing you can say legitimately is the log of some positive number. That's okay. So the domain is just all numbers which are strictly greater, all x is greater than 0. If you'd like interval notation, just go to infinity, or if you'd like the r plus for positive real numbers. That's a plus. All right. Okay. So now, looking at the graph, what can we say about the range of the log function?
The range is all real numbers.
Yeah, so for any point on the graph, or for every y value on the y-axis, right, wherever it is, whatever y is, there's always you can always draw a horizontal line and you'll meet the graphs of the log somewhere. Okay, so all the y values are covered by the log graph, so to speak, so the range is all real numbers. Or the number line, or R. Awesome. All right, so then we want to make some notes. Yes, Nina?
I have something to add on to this. When you say
Yes.
an exponential function, the domain is all real numbers and the range is anything greater than 0. In a logarithmic function, it's the opposite. It's
Yeah,
the inverse of
that
an
is an
exponential
awesome
function.
observation, and we'll go ahead. We'll summarize that as well after we make some notes. But that's very good. That's because log and exponential functions are inverses, so you expect the range of one to be the domain of the other, and vice versa. That is correct. So notes. Okay. When is log 0? Well, that's when x is 1. And noting Newton's observation, notice how that compares with e to the 0 being 1, right? It's a side note. Okay. When is log positive? Well, the graph is above the x-axis. When x is greater than 1. And when is log negative? I have this bad habit of switching from cursive to cursive whenever writing log. I don't know why. Okay. Well, that'll be the graph is below the x-axis, where x is between 0 and 1. Awesome. Awesome. So for x is between 0 and 1, you can also use interval notation. Okay. All right, so now we can also note the long-term behavior, or asymptotic behavior. So you see the game here. We're going to say, we're just going to complete the phrase as x goes to positive infinity. Log does what? The same. Awesome. Or you can say log does the same. I like that phrasing. And log infamously, right, grows very slowly. Like eventually any polynomial, any like square root or whatever will outpace the growth of log. But nevertheless, even though log grows very slowly, don't be fooled, there is no horizontal asymptote somewhere. Eventually, the log will be as large as you need it to be. Just very slowly. Yeah, awesome. Okay, and so what happens as x goes to negative infinity? Well, or rather, what's wrong with me saying x goes to negative infinity here? What happened? It doesn't. Thank you. Like the log doesn't exist for negative x's or 0, right? There's no long-term behavior if x goes to infinity. However, we could consider what happens as x approaches 0. And just to be completely legitimate, because log only exists to the right of 0 for positive x's, you can say as x approaches 0 from the right. Again, a distinction you'll soon kind of like x approaches some number from the right, from the left, and you want to describe the behavior of your function. So as x approaches 0, log x does what? So yeah, so looking at the graph blows down, right? So as x gets close to 0, the y value, so you see the graph goes down. So the y values go to negative infinity. And you'll be formalizing this kind of analysis, which necessitates familiarity with these functions in terms of the language of limits and so on. Yeah, I mean, if we look at points on the graph, you see that the x-coordinate is getting close to 0, and the corresponding y-coordinate on the graph is getting more and more negative, right? So we say that as x approaches 0 on the right, the y values for your log function go off to negative infinity. Okay. Any question? We will, Ninat, as you mentioned, we will go into how we're going to compare the log and the exponential, of course, the inverses. Look at the relationship. But for now, I just want to do some examples. Maybe I'll just do one because it looks like I still need time for trigonometry. So here we have our function is a natural log 2x squared plus 3x plus 1. Right? And we want to know like the standard stuff. What's the domain? So where is the function defined? Which, of course, is the same thing as asking where it's not defined. It's the same information. Where the function is, I guess, 0, right? And then once we know everywhere the function is defined, we know it's 0. Everywhere else, because it's a continuous function, everywhere else the function will either be positive or negative. Standard kind of calculus there after you do the actual calculus. All right. All right, so how would we reason about, what kind of reasoning do we use to find the domain here? Well, we're dealing with a log function, so we know that we can only compute, we can only take logs of positive numbers. So the domain, this is the same thing as asking when is this polynomial that's inside our log, when is it positive, right? So how would we find when the inside of our log function is positive? Well, it's when it's greater than 0. So again, it's kind of like stepping back to polynomials. We first actually want to find where the polynomial is 0, so as to cut up the number line, then maybe the resulting interval which is test points. And we would factor, that's right. Or if you'd like, you can just factor. So yeah, this factors, I believe, that's it. 1 and 1. All right. Okay, so we factored, and we see that the product is 0 as soon as one of the factors is 0. So either 2x plus 1 is 0 or x plus 1 is 0. So in the first case, x would have to be negative 1/2. In the second case, x would have to be negative 1. So you've taken the x-axis and cut it up to 3 subintervals there. 3 regions. Okay. And then we can use test values. So maybe like a -2 for the interval from -infinity to -1. And then plug that into our factors. So 2x plus 1 would be negative if x is -2. And the second factor, x plus 1, would also be negative. All right. So at the end of the day, that's positive, right? Okay. So it looks like this interval from -infinity to -1 is part of the domain because it's positive and we can take natural positive numbers. The middle interval, I believe, is let's say we take. Let's put it up a little bit. Suppose we take. Well, give me a number between -1 and -0.5. No, we are not determining whether the function is negative or positive. We're actually just looking at the domain, which is, and the function is a log, so the domain has to be positive. So it's like its own little separate problem where we have to find where the inside of our function, right, the inside of that log, where it's positive or negative. So it's like, I guess inception is no longer a reference people use. It's like, it's 2 levels. The -3/4 is very good. I like that one. Halfway between -0.5 and -1. All right, that interval. All right, so the first factor would be, let's see, 2x plus 1 when x is -3/4. It's going to be -3/2 plus 1. So -1.5 plus 1, that's -1/2. Yeah. So the first factor would be negative. And the second factor would be, well, positive, right? It's a positive quarter. So positive. So negative at the end of the day. Yes. We first, so the question was, like, what do we, were 2 test points to plug into this polynomial. Right? So we first found where the polynomial is 0, and that happened at 2 points, 2 of the x values. So from everywhere else, we can just choose a random test point, plug it into the polynomial to test whether it's negative or positive. And then let's say something greater than -1/2, like 0, that works. So the first factor would be 1, positive 1, and the second factor is also positive 1. All right, so to answer the first question, what's the domain of a function? Well, it's a log. It's when the inside of the log is positive, so strictly greater than 0. And we found by looking at the inside, which is a polynomial, that the polynomial is positive. On the interval from -infinity up to -1, not including -1, or and, whichever way you want to phrase that. All right, maybe we'll skip parts for time's sake. We're going to skip these 2 parts, but part 2, let's do that. Oh, that's a great question. I was just, so why is there a dotted line? I just wanted to make sure that I cut up the number line and it's clear to everybody. So I just used these. There's no reason. I thought I was making things clear. I was wrong apparently. So I just wanted to cut up the x-axis using the dotted line. Okay, so part 2. Right. When is this function equal to 0? How would we reason this? Yeah, right. So we know that log is 0 whenever the inside of log is equal to 1, because log of 1 is 0. That's one of the observations we made about the logarithmic function. So this, all we want to do now is take the inside of our log and set it equal to 1, and then solve for x. Here we can factor an x out. And so this is 0 whenever x is 0, or x is negative 3/2. Okay. You do need to make sure, though, that these values of x are in the domain of the function, right? Because your log cannot equal anything if it's not defined. So, but x equals 0 is in the domain. It's in, it's in here. And x equals negative 1.5 is in the domain as well. So both of these are solutions. With logs, you probably want to go check. Okay, awesome. Now I was going to ask some other questions, but I'll let your professors introduce some of the other ideas. Okay. All right. So what is the relationship between log and the exponential? Well, they're inverses of one another. You can kind of see that graphically. Here's a log. Sorry, here's exponential function. And then there's the log function. So does anybody remember if you graph a function and its inverse, what kind of symmetry you expect? Symmetry about what line you would expect?
Y equal x.
That's right. So the graphs of inverses should be mirror images about the line where y equals x. So that kind of basic diagonal line where y equals x. So exponential and log are inverses of each other. Okay, and so this is next to, we can maybe discuss the observation that a student made. Namely, that if you have an exponential and you look at the domain and the range, and compare that with the domain and range of the log, well, the domain of e to the x is all real numbers. The range is just positive numbers, as you see from the green graph. So these being inverses, the domain and the range will be interchanged. So if the domain of the exponential function is all real numbers, then the range of its inverse will be all real numbers. And right, if the range of the exponential is positive, then that means the domain of log must be positives. Okay. And since these are inverses, we get the equations where e of log x is equal to x. Right? If you compose inverses, you just get the argument back. So you just kind of get, they kind of annihilate each other, if you will, to use a sort of dramatic words, I guess. And this will be true for all, well, nuance for all for x's which are positive, of course. right? Because we have log of x, so x has to be positive. And likewise, if you compose the other way, so log of e to the x is just x for all x's, regardless whether it's negative or positive. Okay. So let's look at, maybe I'll do, I'm going to skip I have 3 examples. I'm going to skip one of them. So here I'm going to instead, let's say, solve for x in the following equation. And these are really basic. You just want to get the basic problems for the essential ideas. So we're going to solve for x in this equation. I could have written this as like a polynomial in log x, right? I mean, as a side note, I could have said that this is log x squared minus 3 log x minus 10, right? And then you'd have to recognize this, that this is the polynomial in log x. Okay. But again, to solve for x here, it's already factored. That means that either the first factor is 0 or the second factor is 0. All right. And so first fact, that's the first statement is the same as saying log x equals 5. And so if you want to solve for x, or some function of x, and inside a log, you have to undo the log by exponentiating both sides. So you're composing with the, right? These are now exponents. They're equal, right? So e to the first exponent on the left should be the same as e to the exponent on the right. And these are inverses, so you just get x on the left. All right. And is this a valid value of x? Yeah, it's positive, right? Exponential is positive, so x needs to be positive, by the way, right? On the second case, we have log of x has to be negative 2 after subtracting the 2 over to the right, and then we exponentiate both sides. And to get x from inside the log, and is e to the negative 2, is that a valid solution? I'm doing the log, I'm just made it up, I have no idea. But you make both sides like powers in the exponential, right? You exponentiate. I'm like a child who's extending, like, I don't know. Language used to novel situations, exponentially. Yeah, it's valid, right? Because again, e to the whatever is always positive. So x has to be positive, so that works. Right? So both are valid solutions. For the next simple problem, here, I don't know what to call it, take the log of both sides. I think this is the phrase I'm going to be using. But we're going to solve for x again. In the equation, e to the 2x minus 100 is 0, right? Just basic idea. We need to solve for x. We need to isolate x on one side of the equation so that we know what x is. But x is an exponent, so we're going to use the fact that log and the exponential are inverses. I apologize if this is too easy, so now we're going to take the log of both sides. I don't think there is a word for it that's commonly used without feeling very pretentious, like I don't know. Okay. So yeah, log of e always just returns the argument. So 2x equals log of 100. Therefore, x must be, well, yeah, log of 100 divided by 2. Which, by the way, is the same as natural log of 10. Okay. All right. What else can I say? What did I? Oh yeah. Well, notice that do you see how the left side of that equation is really a difference of two things squared, right? E to the 2x is the same thing as e to the x squared. 100, of course, is 10 squared. So this is literally a difference of two things squared, so it factors into a product of the conjugates there. Would this give us other solutions, this approach? I don't know what the process is called. It's just the idea x is an exponent. You need to solve for x, so you need to decouple it from the exponent, right? So to move x away from the exponent, you have to take the log of two sides of an equation. Taking the log of both sides of the equation. Change in the base. Doing the inverse operation, yeah, all these phrases I think are good. Probably better than mine, take the log. All right, let's see. But this, if we factored the left side first, right, we would say that e to the x minus 10 is 0, or e to the x plus 10 is 0. And indeed, the first case, e to the x is 10, get rid of the exponential, right, by taking the log of both sides, and we get the answer that we had before. But for the other case, we get e to the x equals negative 10, which, yeah, okay. You see the problem there, right? So that would give us an extraneous solution. This is not defined. Oops, right? This is wrong. Not possible. You can't take the log of a negative number. So we still get the same solution as before. I don't know why I just saw that and decided that it would be worth mentioning. All right. Cool. So 208, maybe we do need to discuss the properties of logs. Hey, if anybody needs to like walk away for a while, I might take like a 3-minute break. I'm to go to the bathroom. Do you guys mind? Well, it doesn't matter. I don't care if you mind. I'll be back like in 3 minutes. You just need to run to the bathroom. All right. Oh, all right. So properties of logs. Right. So log. Historically, this was really useful, right? Log of a product, right? So log of A times B. Hope there's no mistake. But that's two things multiplied. Is the same as log, the sum of the logs of the two factors. So log turns multiplication into addition of logs. And so that's why they used to have historically logarithmic tables, right? Because it's more work to multiply two numbers than to add two numbers. So if you want to multiply A and B, you'd use a log table to find what the log of that is, right? Hold on, what am I saying? It would be easier to find the log of A in a table and then find the log of B in a table. Add them because that's cheaper, right, in terms of effort. And then take the inverse log using the log, so exponential. So I don't know, there's some hyperbole that it saved so many lifetimes for astronomers after they started using logs. All right, number 2. Log turns division into subtraction of logs. Log of the numerator minus the log of the denominator. And finally, this very useful property, log of something to a power, actually brings the power in front. So that's extremely useful if you need to bring down an exponent from a base because that exponent has like the variable you're trying to solve for. And these properties hold for logs of any base. By the way, in biology or chemistry, what's the base that we typically use for logs? And so this is whatever the wet sciences, right? And maybe computer science. Right. What base do you tend to use for biology, chemistry? Log base 10, because decimal system. And for computer science, what's another base that you like to use? Computer science bits binary. So you often see log base 2. Anyway, just a side. We're using base E. Awesome. Okay, so what this will be used for is before you do calculus, you sometimes want to make that calculus easier by taking advantage of these three properties of logs. Maybe some of the previous properties as well. Maybe your high school teachers made you do something crazy like this. Where you're supposed to use properties of logs to expand this completely. In calculus, it will be much easier to do calculus on a bunch of terms separately than to do calculus on this mess right there. Sorry, log. This is log of this mess. So you first notice that property, first you probably use property 2, right? Because you've kind of conceptualized this as a numerator divided by the denominator inside the log. So you're going to take the log at the top. The log turns division into subtraction. Log of the top minus log of the bottom. And by the way, let's not fool ourselves in calculus. Roots, we know, are powers, fractional powers. So the fifth root of that expression is the same thing as that expression raised to the power 1/5. So go ahead and include that. Yeah, I don't know. And all this stuff, yeah. This is as exciting as, it's the same level of hype as folding laundry, right? But it's necessary, so. All right. Then in the first term, then we have a log of a product, right? So x times something. So we know log turns multiplication into addition of logs, so. And for the second term over here, notice I can take the 1/5. That's an exponent. I can bring in front by property number 3. So I can say that that's 1/5 log e to the 2x plus ex. And using the third property again, the second term over here, bringing out the 2. And I guess we could do something else. I mean, e to the x is a common factor. Right, so we'll have negative 1/5, and log of the product is just the log of the sum of the logs, sorry. All right. I suppose there's just one more thing we could do. Of course, log of e to the x is just x, log and exponential being inverses of one another. And by the way, this does not simplify, right? Notice there is no property. I'm really afraid of even writing this down, but there is no property that says log of a plus b is something. There's no identity, right? It's definitely not log of a plus log of b. So this is not wrong, or I'll just say wrong. Okay. All right. So the idea would be that you'd take advantage of logs, and it's actually much easier to do calculus on each of these individual terms than it is on the original. Peanut, okay, your teacher compared this to peanut M&M of the properties specifically for derivatives. You could say it's similar. Yeah. An onion. That makes it makes you cry. Maybe you can do that peeling an onion. You're just supposed to leave the two. I'm a little confused. So, okay, you can tell me, Safa, if you're referring to this, where I factored out a e to the x. Yes. Okay. Well, e to the 2x, as we noted, is the same thing as e to the x squared. So I would think of that as two factors, right? E to the x times e to the x. So e to the x is a common factor, which I factored out. And after I did that, right, from the first term, I'm left with e to the x. From the second term, I'm left with an implied 1. So no, I was right. I think I'm right. That's okay, cool. So you'll be doing this often, taking advantage of these properties before you actually do the calculus. So here's another use of, so again, soon enough, when doing limits and derivatives, you're going to get situations like this where you don't have like a power function like x squared. So that's a polynomial-like thing, right? A power, or y equals, let's say, x to the 1/3. Right? So notice here that the variable here is the base, and the exponent is constant. We have rules for using calculus on such functions. You have other functions where you have like a base, which is a constant, and it's the exponent that's the variable. So these guys are called, so I guess these guys would be, algebraic. But these guys are called exponential. They're two different species of function, right? But we have rules for calculus for both of these. What you're going to encounter is some crazy stuff like x to the power x, right? X to the power x. So that's neither like a power function algebraic, and it's not exponential because both base and the exponent are variable functions of x. All right. So this is what over here. This is what I was referring to. The kind of cases where the base and the exponent are both some expressions in x. And so for those cases, you're going to take advantage of logs, in particular property 3, right? You want to decouple that function of x from the and the exponent from the base, which is also a function of x. So an example that you will see, sine of x maybe to the power 1/x, right? What you're going to end up doing is just taking the log of both sides before any calculus. Because now this exponent using properties of logs can go in front. And now you can use some other rules of calculus, which called product rule and so on, to actually do some stuff. So that was another case you're going to be using properties of logs. Oh my gosh, okay. Maybe I'll mention something about logs in general. So these two expressions, like log base 2 of 8 equals 3. Why is that statement true? Well, what's the correct notation for this? Yes, because that's equivalent to saying 2, the base, right? 2 is the base, to the power 3 on the right-hand side is the same as the argument over log. They're in fact the same pieces of information, just written 2 different ways, 2 kind of inverse ways. So if you say log base b of x equals y, that's exactly the same thing as saying b to the y is equal to x, right? So if you want to maybe use your on your calculators, if you maybe don't have a calculator which allows you to choose the base of your it doesn't let you choose a base. If you want to compute like log base 5, and that's equal to some number, you could use a change of basis formula or base formula, but we can rewrite this as saying that 5 to the power x should give us 30. Beautiful. All right, and now if you want to solve for x, you can just use property 3 of these properties that we wrote down for logs. We just take the log of both sides, okay, which allows, so x is the exponent, which by properties of logs can go in front of the log. So we've decoupled the x from the exponent there, from the base, whatever, I don't know how to say that at the moment. So then we divide both sides by natural log of 5, and voila, right? Now we know what x is using a log function, natural log, which our calculator most likely has. I guess this does simplify it. 30 is 6 times 5. So log of 6 times 5 is the same as log of 6 plus log of 5. I don't know. So I guess we could write our answer as log of 6 divided by log of 5 plus 1. All right. Now I'm going to skip this next example so that we can, at least to get some basics of trig. Right, so we have exponentials, logs, and now the other important transcendental functions are sine, cosine, and those other related functions. Okay. Do you guys have any comments or questions at this point? All right. So for trig functions, you do have a question. Yeah, log of 5 divided by log of 5 is indeed 1, because a number divided by exactly the same number is 1, except, of course, that number is 0. All right, so in your pre-calculus courses in high school, did you guys use like degree angles? So when you measure angles, did you guys use radians or degrees? Both, okay. Okay. So in calculus, it turns out that even though in physics and engineering courses they'll still use degrees, in calculus, radians are preferred. So we probably need to know how to go back and forth between the two. So if you have a angle measure in radians, how do you convert that to degrees? Well, we know that for every pi radians, we have 180 degrees, right? So this would give you the angle in degrees. And going the other way, if you have an angle that's measured in degrees, you know that for each 180 degrees, that's the equivalent of pi radians, right? Yeah. And the reason, like, in physics and stuff uses radians is because it relates angle measures to lengths. So if you have a circle of some radius, let's say radius r, let's use 5, and you have some angle, let's say 30 degrees or something. Okay, so, all right, fine. Like often we want to know like what the length along the circumference is for that angle. Like, you want to know that length. Okay. And so we know that let's call that length S. So we know S is the radius of the circle times the angle measure, right? However, for this to be valid, this angle has to be in radians. Right, so radians relate angle measures to lengths in your lengths. So for example, all right, if this you want to know this length S, this is wrong. We wouldn't say that this is 5 times 30 degrees. It makes no sense. So this is wrong. Instead, we would have to use the appropriate radiant measure, which is pi over 6. So it would be correct to say that the length along the circumference there is the radius times the angle measure, but in radians. All right. And of course, we know the basics here of trigonometry. You typically learn it first with just a right triangle where all the angles have measured less than 90 degrees or pi over 2 radians. And we have a hypotenuse side, an opposite side, and an adjacent side relative to that angle. So of course, I'm going to relate this to the unit circle. So instead of opposite, I'm using y, and instead of adjacent, I'm using x. Instead of hypotenuse, I'm using r. Okay. And of course, we know that according to the Pythagorean theorem, the hypotenuse squared is just the sum of the two smaller sides squared. Okay. And then sine of that angle is going to be a ratio of the opposite side to that angle and the hypotenuse. So opposite over, I believe there's a word for that, right? There's a way of remembering that, Sakatoa or something like that. So sine is opposite divided by hypotenuse. Cosine is adjacent over hypotenuse. So that's the part of the Sakatoa. And the tangent is just the sine over cosine. So you'd say it's y over x, or opposite over hypotenuse. Sorry, opposite over adjacent. So that's part of the tall. And so sine and cosine are like the building blocks of your trig, right, functions. Tangent is just sine over cosine, so it can be constructed out of those. And then you have the reciprocals. So the reciprocal of sine is called cosecant. So that would be hypotenuse over opposite side. The reciprocal of cosine is called secant, without explaining why, which is more fun. And then the reciprocal of tangent is cotangent. Okay, so we know those basic definitions. And if you know any two right triangles, you need to know the 30, 60, 90 triangle. So you have 30 degrees. Of course, that would be the smallest angle. The middling angle is 60 degrees, and the largest angle is the right angle there. In radians, 30 degrees is pi over 6. 60 degrees is pi over 3. And if I tell you the lengths of the sides are 1, square root of 3, and 2, well, 1 is the smallest number there. So 1 must be the length of the side opposite the smallest angle. 2 is the largest number, so it must be the length of the side opposite the largest angle, meaning pi over 2. And then this is the middling side, so it must be opposite the middle angle. Okay. And then using this, you can, if you know this 30, 60, 90 triangle, as they say, you can figure out a lot of the basic trig functions that we're going to see in the unit circle. It's the sine pi over 3. Relative to the angle, its opposite would be square root of 3. Hypotenuse is 2. And what's the other? Oh, the sides. I was just thinking that 30 is the smallest angle, 60 is the middling angle, 90 degrees is the largest angle. So if the lengths of the sides of this 30, 60, 90 triangle are famously known to be 1, square root of 3, and 2, then you know that the shortest side is must be opposite the smallest angle. So 1 must be the side opposite the smallest angle. Square root of 3 must be opposite the 60-degree angle. Yeah. And then, okay. And the other kind of basic triangle that you probably learned in high school that's useful in starting to think about unit circles, the 45, 45 triangle. So it's a right triangle. That's also isosceles, right? Because the two sides opposite the equal angles are equal. And so we think of that as the two smaller sides being 1 using the Pythagorean theorem. We figure out that the hypotenuse must be square root of 2. So you can use that to find like sine of 45 degrees, cosine of 45 degrees. So that would be a good starting point. And now maybe the next example is going to be useful for math and physics. using this idea. If you know an angle and a right triangle, let's say pi over 3, and you know one of the sides, let's see the hypotenuse, then you can find the other two sides, right? Using trigonometry. Let's call the opposite side y and the adjacent side x. So we know that sine of theta is opposite over hypotenuse. So we see that the opposite side would be the radius r times sine theta. You'll see that in physics all the time when resolving vectors. And likewise, cosine of theta is the adjacent side divided by the hypotenuse. So solving for x, you'll see that x is the radius times cosine theta. So we'll see that the opposite side can be expressed as the radius sine of pi over 3. And then you'll have to know that sine of pi over 3 is square root of 3 over 2. X is radius times cosine, which we know cosine of pi over 3 would be adjacent over hypotenuse, so 1/2. Okay. And sometimes we do this a little bit more abstractly. So sometimes you have a right triangle and the sides are variable length, right? So let's say this side is x, this side is like x plus 2. And we label one of the angles theta. And we would like to express, let's say, tangent of theta as a function of x. So we want to express tangent of theta algebraically. I mean, this is kind of both. If you relate, so are we going to be dealing with rectangular and polar concepts? Well, this is what it is, right? We are relating rectangular coordinates, so x and y, and we're relating them to polar coordinates r and theta. You'll definitely be seeing that, at least in calculus. You'll be seeing that in calculus. Starting with calculus. This is not a class. We do not have assignments. It's all voluntary. So sometimes you want to express like a trig function of theta as an algebraic expression of the sides of your right triangle variable. Well, that's simple enough, right? Sine of theta and cosine, sorry, tangent of theta is opposite divided by adjacent. All right. But what if you wanted to know, let's say, cosine of theta? What would you have to do first? So you're going to see this in something called related rates problem, where you're going to have, like, they tell you that x is changing length with respect to time, right? And then you need to find at what rate the angle is changing as well. So you're going to need to relate angles to side measures. So this is one of the skills you'll be using in Calculus 1. Well, so if you want to use cosine, right? If you want to find cosine of theta as a function of x, you're gonna have to know the hypotenuse. So you just use the Pythagorean theorem, right? The hypotenuse is the square root of the first side squared plus the second side squared. Now, once you use the Pythagorean theorem, you can use your knowledge of trig to express cosine of theta as a function of x. Cosine is adjacent side relative to angle theta divided by the hypotenuse side, which you can multiply out if you'd like. So you'll be doing that. Okay, but we want to also discuss the unit circle, so let me see if I have one. One second. So I guess if you want to do any homework or an assignment, and it's not, I mean, nothing's due, you please learn the unit circle. So the first thing we can talk about is getting the angles. So we can think of learning the angles or revisiting them as maybe cutting up pi into fractions. So if you have an angle, what angle associated with a straight edge? The line. Like how much angle do we have in a straight edge? Right. That's pi. It's 180 degrees, yes, but it's pi radians. So despite the word, right, it's not a full pi. It's half a circle. So we associate the straight edge angle measure of pi radians. Okay. And to go all the way around, you go 2 pi. All right. And now if you want to, maybe you can break up, you can traverse the circle by taking quarters of pi, right? So I'm actually use red then. Okay. So we can say that this angle here is 0. Okay. And if you take since we're cutting pi up into quarters there, this would be the first quarter of pi. This would be the second quarter of pi, which of course reduces to pi over 2. This is now the third quarter of pi. We're just counting up by quarters. And this would be the fourth quarter of pi, which reduces to pi. And then you can keep going. You can add an extra pi, a quarter of pi. So it would be 5 quarters of pi, 6 quarters of pi, which reduces. And then, well, 6 quarters of pi, so this would be 7 quarters of pi, and so on. And back over here, 8 quarters of pi to make a full round, which of course is 2 pi. And then maybe instead of kind of traversing the circle in quarters of pi, maybe we can take 1/6 of pi or 1/3 of pi. Yeah. Hello. All right. So you can cut up pi into 6ths. You should use these as well, doesn't it? Yeah. 1/3. So you can start at 0, and the first 1/6 of pi, then you add the second 1/6 of pi, which reduces to pi over 3. So I'm not probably going to keep doing this. 1/3 1/6 of pi. But the idea is that you want to be able to generate the angles whichever way you feel comfortable. I just feel comfortable adding pi over 6 over and over again. So then the fourth pi is 6. Fifth pi. And so on. And then the 6th pi is 6, it's just pi. And so on. So you generate the angles. Okay. All right. So we also need to know how to relate the trig functions to this unit circle. All right. What do you guys want to talk about for the last 10 minutes? All right. So unit circle is just a circle of radius 1 in the xy plane. Radius 1. We measure the angle from the positive x-axis counterclockwise. It's considered a positive angle measure. I would just do a lot of practice problems, right? I would come to the tutoring lab. It's a great environment. Some people like to use it as a study hall. You get on the fly help from tutors. People like the balance of like your friends keeping you on track and your friends distracting you just the right amount. So that's nice. Yeah, my day is good. And then each point on the unit circle, of course, it's in the xy plane, so it has an x and the y coordinate. As you probably already anticipate, the x coordinate is will be cosine theta, and y is considered sine theta on the unit circle. So we know that the first quadrant, x and y are both positive, so sine and cosine are both positive. So all the trig functions are positive because all trig functions are going to be built out of sine and cosine. In the second quadrant, we see that x is negative, but y is positive. So we can say that sine is positive. So sine is positive, but everything else will be negative, except, of course, the reciprocal of sine, cosecant. And then in the third quadrant, x and y are both negative. So sine and cosine are both negative. So tangent in the third quadrant is sine over cosine, where those are both negative. So tangent itself will be positive. So we say tangent is positive. Everything else is negative. And then in the fourth quadrant, we know that x is positive, but y is negative. X being the cosine means that cosine is positive. But sine will be negative. Right? So, so this acronym there, all students take calculus for quadrant 1, 2, 3, 4 respectively. It's a way of memorizing whether sine or cosine is positive. All silver teacups. Is it because that statement has no truth value as opposed to all students take calculus, which might be true in some cases, which might not be true in others? I don't know. Yeah. I like that. All silver teacups. Sure. Okay. And so knowing the angles and knowing where sine and cosine are positive or negative depending on the quadrant, and then also knowing the first quadrant, you can pretty much generate the unit circle. I don't know what tricks you've learned or the way you've learned to memorize this. But let me mean, here's a way that somebody taught me one time. If you list the angles in ascending order, pi over 6, pi over 4, pi over 3, and finally pi over 2. I think I've seen some students do this with their hand, and then you list integers 0, 1, 2, 3, 4, so the consecutive integers 0 to 4. And then you take the square root of those consecutive integers, and then you divide by 2. After I reduce, what we get is the sine of those angles. And if you write the numbers that you got in that row in the opposite order, then you get the cosine of those angles. So that's kind of one way, if you kind of forget it, kind of muscle memory, getting the sine and cosine of the basic angles in the first quadrant. Add sugar to coffee. That's just wrong, by the way. No, it's not true. You don't have to add sugar to coffee. But it makes sense. All silver teacups, add sugar to coffee. Okay. Right. So the idea is that if you know the sine and cosine of the basic angles in the first quadrant, then you just do reflections, right? So I guess, for example, we know cosine of pi over 3. Let's put this column here. So cosine of pi over 3 is apparently 1/2. And sine is square root of 3 over 2. Great. So the unit circle and look at the other. So using symmetry, we'll see that this point would be now in the second quadrant where x is negative, so cosine of 2 pi over 3 would be negative in half. But we're still in the second quadrant where y is positive, so sine of 2 pi over 3 would be square root of 3 over 2. Anyway. Okay, guys, it's been 2 hours. I'm going to end it there. But I'll go ahead and download the videos, edit them a bit, and upload. So you can find a similar review from previous years on our website. I haven't already posted the link. I'll do it again. Yeah. No, it's not. Elliot's here. Say hi. What's going on, Elliot?
I also uploaded the video yesterday as well as the physics video this morning.
Nice.
And in the video descriptions, I included links to all the work that we did. And I also added links to make sure that everyone can access them. So if anyone tried to access them earlier and they weren't able to, you should be able to now.
I'll post the link to today's review in chat. There you go. That's the direct links to yesterday's review with Elliot, with links to the PDFs. More generally, that our peer tutoring channel has reviews and such from previous semesters. Okay, we'll see you guys tomorrow. I believe Elliot's going to start introducing you to concepts of limits. Well, awesome, finally some calculus. Yes, Esther? Yeah, by the way, with the trig stuff, we didn't get very far. We're supposed to talk about trig identities. So find a video on our peer tutoring channel. And also inverse trig function. So that was a lot. Maybe use Tim Vicious for 2 hours. Well, yeah, Elliot uploaded yesterday's video, and he says that yes, there's a link in the description of the video to yesterday's PDFs. So, and yeah, they would be available for download. Have a wonderful day, guys.